In the last video, we talked about representations of the elements of this type of group, the permutation of 4 elements as arrays. So one thing that I didn't mention last time, or I didn't go over, was the way in which we find the result of the binary operation between two permutations, given that they have this array form. So I'm going to do it in 2 ways. So let's say we have these 2 permutations in S4. So remember what that means is this is a bijection between the set 1, 2, 3, 4 into the set 1, 2, 3, 4, and this means 1 goes to 2. So alpha of 1 is 2, alpha of 2 is 3, alpha of 3 is 4, and alpha of 4 is 1. So this arrangement that is here represents the function alpha, which is a bijection, and the same thing happens with this bijection here, beta. So what we want to do here is do this computation alpha composed with beta and beta composed with alpha. I'm going to do both of them, but in a different way. Now, if you actually look at the book, this notation is not there. The composition is basically ignored, because when you say alpha, beta without anything, then it is assumed that the binary operation there will be the composition. But I'm going to keep it for now, so just to emphasize that idea. I'll say, okay, so let's do the first one here, alpha composed with beta. So that will be a function. So it's going to be a function that goes from the set 1, 2, 3, 4 into the set 1, 2, 3, 4. That is a bijection just by doing the composition now. If you apply the definition of the composition of functions, so what you have to do here is check what this function does to each one of the elements 1, 2, 3, and 4. So let's check that for the number 1. So what is alpha composed with beta? Apply to the number 1. By the definition of composition, that is alpha, apply to beta of 1. Now this beta of 1 that is here, we can read this information from the array that is here. And beta of 1 is basically saying what is the image under 1 for beta. So that beta of 1 is 4. So it will give me, in this particular case, it will give me alpha of 4. That's because beta of 1 is 4. Now if I want to find the result of alpha of 4, I go back to the array that represents alpha, which is this one. So alpha of 4 is 1. Alpha of 4 is 1 here. So that's going to give me 1. So this gives me 1. The same thing you do for each one of the elements. So you have to do it for 2, 3, and 4. Let me do it for one more. So let's do it for 2. So alpha composed with beta evaluated at 2. By the definition of composition, that would be alpha apply to beta of 2. And we do exactly the same thing we did in the previous computation. Is alpha and then beta of 2. I have to go back to the array. And this is the array for beta. This one. So beta of 2 is 3. So that's going to give me 3 right here. So get alpha of 3. So alpha of 3 here, we'll have to go back to the alpha. So alpha of 3. So in this case, alpha of 3 is 4. So I get 4 there. So I'm going to get 4 here. This is 4. Now in a similar way you do the other ones. I already did those because it's, again, you just do follow the way in which we did the first 2. So then you get for alpha composed with beta at 3 evaluates to 2. And alpha composed with beta at 4 evaluates to 3. Now if you put all that information in array form, so that's going to give you alpha composed with beta. Now let's see the first result here. Remember, 1 is mapped into 1. That is what it says here. 1 is mapped into 1. And for the second part, 2 is mapped into 4. And that's what I have here. 2 is mapped into 4. And similarly for the other ones, 3 is mapped into 2. That is being shown here by this column. And the other one is the same. 4 goes into 3. That's this one. So this will be the array representation of the composition. Now I'm going to do the other one in another way that we could maybe call simpler way. So to do that one, beta composed with alpha, is still a composition that we can still compute the way we did it the other one, but this one is, I think, is a little bit easier because you can use somehow a visual representation in this case. So in this case, what I have here is this is the beta. This is the representation, the array representation of beta, and this is the alpha. So I'm going to put them all together. See that I ignore here the symbol for composition. And the answer, it has to give me an array, and the first row of that array is always 1, 2, 3, 4. So you have to figure out where one goes. So I'm going to start, because compositions, if you look at the way we did the previous one, when you evaluate alpha composed with beta, you always start evaluating with the last one first, with beta in this case. So I'm going to start evaluating here with this one here. So I'm going to see where 1 is mapped. So here 1 is mapping to 2, but now that 2 that is here is going to be the new input for the next array. So it's going to go right here. Now that's 2 is going to map into 3. The reason that's working like that is because this here is alpha of 1 gives me 2, and that result has to be put back into beta. Beta of 2 gives me 3. So the result will be that 1 is mapped into 3. So that will be the result for that computation. So 1 is mapped into 3. The same thing you're going to do with the other one. So I may use another color. So for the number 2, remember you're always going to start here at the last array. So we're going to say 2 goes to 3, that's alpha, and then 3, we follow with 3 goes, so 3 here is over there, and that 3 goes to 1. So then in that case, what we are saying is that the number 2 is mapped, under the whole composition is mapped to 1. So that's going to give us 1 for this one. So 2 is mapped into 1. The same thing you do with the other one. So let me use another color, let's say green. So I'm going to start here at the end. And so in this case, 3 is going to map into 4. So let's do that. 3 maps into 4. And I have to look at 4, what 4 is going to map to. So 4 is going to go up here. 4 is going to map into 2. So what we are saying is 3 is mapped into 2 in this particular case. So 3 is mapped into 2. And we actually know what's going to happen to 4 because I'm going to emphasize this because this has to be a bijection. The numbers 1, 2, 3, 4 have to appear here. So this has to go into 4 basically. 4 has to go into 4. Let's check that. Let's check that that's going to be the case. So let me use yellow in this case. So 4 is going to go into 1. And then we check what 1 goes. 1 is here. So 1 goes to 4. So basically we are saying that 4 goes to 4, and that was the result that we expected. So this is another way, a graphical way to do it. Of course, if the permutations are really big, this is not feasible. In the case of if you have like 20 or 30 elements, you will do that with a computer, of course. But visually, in this case, if the numbers are small, you can do this by hand using this graphical method, if you want to call it that way. Now, one thing that I want to point out is the result here. So we got a result here for alpha composed with beta. We got this array. And for the other way around, beta composed with alpha, we get this one. Now, notice here that those two results are not the same. And that usually happens. Now, sometimes it happens that the compositions are the same, but sometimes they are not. So in general, what this is telling us is if you take two elements of Sn and the binary operation here is composition, that is not an abelian group for n bigger than or equal to 3. So for S3, you can find two permutations, alpha and beta, that are going to have this property. Alpha composed with beta is not the same as beta composed with alpha for S3, S4, and so on. So these groups are not abelian for n bigger than or equal to 3, but for S2 and S1, they will be abelian. And the reason those groups are abelian is because if you think about how many elements S2 is going to have, it's going to have two elements. And one of them is the identity because it's a group. So that group has to be abelian because if you take the binary operation of the identity with anything, it's going to commute, of course. And for S1, there is only one element, that has to be the identity because this is a group. So it has to have the identity. So they have to be abelian, these two. But if you increase the n by a little bit more, 3, then that is not abelian anymore, and is not abelian for any number bigger than 3. So that's another example of groups that are not abelian. Now, the array representation we talked about in the previous video and this one, it can be simplified a little bit more using what we call the cycle notation for permutation. This is a way to express the same permutation, the same bijection, but in a shorter way. So let's look at that. So this is another way to represent a permutation. That's what I just said. So let's see how we do that. So let's look at an example. So the best way to look at this is look at an example and see how we get that cycle representation. So we have a permutation in x6, which is this one. This is just an example. So remember, this is a bijection, alpha, from this set into itself. So it's a bijection here. So how do we get the cycle representation? So I'm going to do this graphically again. So I'm going to start here with the number 1. So alpha 1 is mapping to 3. I'm going to make a picture that's going to look like this. So alpha, once I apply alpha to 1 is going to give me 3, and that's because of this column here. Alpha 1 is 3. Now I look at what alpha does to this number right here, to the one that I had from the previous computation. So 1 goes to 3, and then I'll look at what happens to 3. Now 3, according to the definition of alpha, alpha of 3 is going to be 6. So I'm going to put another arrow, put it in a cyclic way, and I'm going to use this notation. So what I'm saying here is that alpha of 3 is equal to 6, which is here. Now I follow the change here. So what happens with 6? Alpha of 6 is 1, so this happens to go back to the same number 1. So this graphical representation is telling me that alpha of 1 is 3, alpha of 3 is 6, and alpha of 6 is 1. So I have the numbers 1, 3, and 6 here. We could keep doing this same exact type of algorithm until we cover all the numbers from 1 through 6. So we already covered numbers 1, 3, and 6. So let's go into the number 2. So let's see what happens with 2. So with 2, so let's look at 2 under alpha. Alpha of 2 is going to be 5. So apply alpha of 2, and that gives me 5. And now I look at what happens with 5. Okay, I erased the 5 there by accident. So 5. So now let's look at what happens with 2, 5. This one. So 5 here, alpha of 5 is 2, so it goes back to the same one. And then if you keep doing that, then of course you're gonna get 2, 5, 2, 5. So we already cover 1, 2, 3, and then we still have to do the 4. So let's do 4. Let's see 4 here. So what happens if you apply alpha to 4? So alpha of 4 is 4. So we're gonna indicate that with an arrow that is pointed to itself. Now, if you look at this type of, again, graphical representation, we cover all the elements 1, 2, 3, 4, 5, 6. So they are here. 1, 2, 3, 4, 5, and 6. Now, this is not yet the graphical representation or the cycle representation here. So for every one of those type of actually cycles, if you want to call it like that, we're going to use this notation. For this one, for the first one right here, for this one, let's use this notation. So we're going to say here, so we started with 1, comma, 1 is mapping to 3, and 3 is mapping to 6. So this notation is going to represent the fact that under the function alpha, alpha of 1 is 3, alpha of 3 is 6, and alpha of 6 is 1. So it's making that representation of this graphical notation that we have here. The same we're going to do for the next one. So for the next one, we do the same thing. So for this one right here, we're going to make this representation. So it's going to be 2, comma, 5. So that means 2 goes into 5, but then 5 goes into 2. So I'm going to close that with a parenthesis. And for the last one, the very last one, this one right here, that's going to be 4 goes into 4. So that is just going to be represented like this. Now, the whole representation of this bijection here is going to be like this. So then we're going to just represent the bijection alpha like this. It's going to be 1, 3, 6, 2, 5, and then 4. Now, whenever you're doing this type of representation, you always have to be careful what they mean. So again, alpha of 1 is 3, alpha of 3 is 6, alpha of 6 is 1, alpha of 2 is 5, and alpha of 5 is 2, and alpha of 4 is 4. So that's going to be the representation and the cycle notation. Now, there's one more important thing that I want to talk about here for this representation. This element that goes into itself is what we call a fixed element. So this is a fixed element. A fixed element is an element that maps into itself. So in this case, what we are saying is that alpha of 4 is 4 again. Now, one more way to reduce this notation is whenever an element is fixed, you basically ignore it from the representation. So the fixed elements are ignored from the representation. Let me write that down. So let's say fixed elements are ignored. Are ignored from the representation, but not ignored on what they mean. If it doesn't appear in the representation, it means that it's fixed. So basically, we're gonna say that alpha is just 1, 3, 6, 2, 5, like this. And then, of course, you have to make explicit here, because the context now is going to be important. You have to say this is an element of what symmetry group. So this is an element of x6. So if it is an element of x6, then from this representation, you will know that we ignore the 4, and the reason is because that element was fixed. So if you ignore this, it doesn't take away the information here. So if it's not there, I know it's fixed. So it's just basically a way to save a little bit of representation. So this is actually the representation we're going to use from now on for permutation, because this is much better than the array. It saves a little bit more time, if you want to think about it that way. Now, if you look at what we had here, we arrange the elements in a way that one maps into the other, and it closes what we call a cycle. So this is what we call the cycles here. Now, I hope that was clear. So now let me give you a definition here. So those kinds of cycles have a special names. It's called cycle, I just said. So a permutation that has this form, like this, is only like this. So meaning that A1 goes to A2, A2 goes to A3, and so on until AM, and AM will map into A1. So this is what we call a cycle of length m, because it has m elements here. Or we just call it an M cycle. So a cycle of length M or M cycle, they are the same. So let's look at an example. So in S4, so we are assuming that we have a permutation of the elements 1, 2, 3, 4. This is a 3 cycle actually. So this is going to be a 3 cycle. And it's a 3 cycle because it's a cycle that has 3 elements. So you have to read what this actually means. Remember, this is just a representation. If we read this in what it means for the permutation, you see here 1 is not there. If it's not there, it means that 1 is fixed. So that means 1 goes into 1. Now, for this one, 2 is mapped into 3. So I'm going to put that in here. 2 is mapped into 3. 3 is mapped into 4. That's going to go here. And finally, 4 is mapped into 2. So that's going to put that here. So these two things are 2 different representations for the same object. And the object here is the bijection that does this kind of assignment. So that would be the same thing. Now we represent it usually like this because it's shorter to write this than writing this array. So that's why we're gonna use basically the cycle representation. Now when you have, again, cycle representation, there is a way to maybe make things a little bit easier when you need to do the composition. So let's look at that. So composition can be done using the cycle notation. So let's look at this example. So let's say we have alpha here, which is this permutation, and beta is this other permutation, and both of them are elements of S5. So they are bijections of the elements 1, 2, 3, 4, 5. And this is what the each permutation is defined. So here 1 goes to 2, 2 goes to 1, 3 goes to 4, 4 goes to 5, and 5 goes to 3. And the same idea for the other one. So in this case, let's try to do this computation. So let's do alpha composed with beta, and beta composed with alpha. Now, I'm not going to do this with an array. I'm going to do it directly using the cycle notation, and it's going to be quite similar to the one we did with the array. So let's do this one here. So we're going to do first alpha composed with beta, this one here. The first thing you want to do here is basically write down the permutation. So this one here is alpha, and this one here is beta. Because we are doing a composition, we're going to always start with the last one here. How do we start this? So this is going to be equal to, we're going to have to know where 1 goes. So how do we start this type of computation? So I'm going to start here, because we have to apply this one first. This one is beta, so it's going to be beta of 1. So what happens with beta of 1? Now, if you think about this as a single permutation, this does nothing to 1, so it fixes 1. When it comes to this one, then 1 goes to 2. So alpha beta of 1 is 2. Now this result is going to pass to the next one. So that's 1 goes to 2. Now let's see what 2 goes. So 2 is being fixed by this, and then 2, remember this is 1 goes to 2, 2 is fixed here, and now 2 goes to 1. So basically what that is saying is that 1 is being fixed, because if you apply 1 all the way through, is being fixed. So in this particular case, what we have is 1 is being fixed. All right, so I need to open another one, and let's see what happens to the number 2. So with the number 2, we start the same way. So we're going to start right here. 2, this means that 2 is being fixed, so that thing happens to 2. But when we come here, we see that 2 is now mapping to 3. Now I have to take this 3 and pass it to the next one, so 3. If we pass it to this one, then 3 goes to 4. So now it's 4. Now take the 4 and pass it to the next one, 4 gets fixed. So that means 2 goes into 4. Let's do that again. 2 is fixed here, 2 goes to 3, 3 goes to 4, and 4 is fixed, so 2 goes to, again the same thing, so 2 goes to 3, 3 goes to 4, so 2 goes to 4. So that's what we have here, 2 goes to 4. Now we have to check what happens with 4. So let's follow the idea here. So start with 4. Why do we get 4? Because that's where we end up with 4. So let's start with 4 here. So 4. 4 goes to 5 here. Now I have to pass the 5 into the next one. 5 does not get affected by this one, but it's going to be affected by this. So 5 will go into 3. So, and then 3 is going to be fixed by that. So 4 will go into 3. Now I have to complete the cycle. So let's see what happens with now. So let me write down again that 3 here. So let's see what happens with the number 3. So if you do it here, 3 for this one, 3 is fixed here. Now it passes to this one. Now 3 goes to 1. Now I pass this 1 here, it's fixed, and now 1 goes to 2. So 3 goes to 2. That completes this cycle. So that's gonna give me that. Now for the other numbers are gonna be fixed. So we have so far 1, 2, 3, 4. What happens with 5? 5 is also going to be fixed. Let's see why. So if we look at 5 here, 5 is mapping to 4. Now I pass 4 here, is fixed. And 4 here is go to 5. Now 5 is fixed here, so 5 will go to 5. Let me do that one more time. So 5 goes to 4 here. 4 is fixed here, and 4 goes to 5. So 5 is also being fixed. And remember, whenever you have something that is being fixed, you basically ignore it. So then we're going to have the representation 2, 4, 3. Now, same thing we can do with the other part. So with beta composed with alpha. And let's practice this a little bit more. So let's look at this one. We're going to do exactly the same thing as we did with the other one. So this is the other way around, beta composed with alpha. So this is beta here, and this is alpha. So we're going to start again with the same thing. So we start with 1. Right. And let's see what 1 is mapped. So we start with 1 here. 1 is fixed by this. Now 1 is passed to this one, so 1 goes to 2. And now 2 is fixed here, and then 2 goes to 3, so 1 goes to 3 in this case. Now I need to know where this 3 is being mapped. So I start here again, 3. This one here, 3, is mapped into 4. 4 is being fixed here. 4 goes into 5 here, so we add up to 5, and 5 is being fixed, so that's going to give me 5. Now I still have to know where 5 is being mapped to, so start here again, 5. 5 goes to 3 here, 3 is being fixed here, it's being fixed here, and then here 3 goes to 1, so that means it's going to complete this cycle here, so then that's going to happen. Now, for the other ones, 2 and 4, you can actually check that they get fixed. So 2 and 4 will be fixed. Let me just do 1. So for 2 here, what happens? So if I apply the 2 here, this is fixed. So 2 goes to 1. 1 is fixed here. And then here 1 goes to 2. So 2 goes to 2. So 2 is being fixed. And the same is going to happen with 4. So we get this result. Because remember, whenever something is fixed, we don't write it down. So we have these 2 permutations. Again, we get the same thing, that alpha composed with beta is not the same as beta when it comes composed with alpha. Sometimes it happens that they're the same, but in this case, it didn't happen. In any case, we always say that S6 is not abelian. Any permutation group that has an n that is bigger than or equal to 3 is not abelian. So that's how you do the operation using the cycle decomposition. Now, this theorem is something that I actually already mentioned, and is that every permutation can be written as this, as product of cycle. And it's more than that, it's a product of disjoint cycles. So every permutation that you can think of in any Sn can be written as a cycle, or just one cycle, or is a product of disjoint cycle. Now, product here basically means is the composition of disjoint cycles. If you think about what that means, we actually already did that, because if you look at this alpha here, this alpha is already written as a product, or to say it much better, composition of 2 disjoint cycles. Disjoint cycle basically means that this cycle and this one do not share any numbers. So 1, 2, 3, 4, 5, they don't share anything, and the same happens here. So this is a product of disjoint cycles, and every time you have a permutation in Sn, you can always write it as a product of disjoint cycles. How? Let me go all the way back to the first part where we were looking at the way we represent cycles, which is this one. So if you start representing cycles, permutation as cycles in this way, the way we did it in this video, you will always end up with a product of disjoint cycles. You can always do that. Now, I'm not going to prove the theorem here because the proof of that theorem is quite tedious and is quite long. So if it has all those two things, I'm not going to do it. If it is tedious and long, I'm not going to prove it. So we're just going to look at this. The proof is in the book. If you're curious about it, it's in chapter 5. And you can check out the proof of that theorem. Now, another theorem that I want to point out in this video lecture is this one. Disjoint cycles commute. So what do we mean by that? So if you have a pair of cycles, let's say you have a cycle alpha, this is only one cycle, A1 through AN. Remember what that means is alpha of 1 is mapping to alpha of 2 and so on. And alpha of n is mapping to A1. And similar for beta. It has m elements. It is an m cycle and this is an n cycle. And they are disjoint. What that means is these numbers here, A1 through AN, they are completely different from these numbers here, B1 through BM. So they are disjoint. There are no common numbers here. If that is the case, if they don't have common elements, then they do commute. Alpha composed with beta is equal to beta composed with alpha. Assuming that they have nothing in common in the cycle decomposition, they will commute. For example, if you have alpha that is 1, 2, 3, that is a 3 cycle, and 4, 5, 6 is another 3 cycle, you can think about these elements as element of x as 6. Then because they are disjoint, because they have nothing in common, they will commute. And the thing that they are in common is this permutation right here. So if you look at this, you're gonna find easily that this actually is the representation of alpha composed with beta and also beta composed with alpha. They are exactly the same thing because they are disjoint. Alright, so that's all I have to say for today. So today basically the lecture was about cycle decomposition and how you compute with those. In the next video lecture we will continue with permutations, and from now on we will represent permutations as product of disjoint cycles. Alright, that's all for today. Take care and good luck.